math people, and welcome to our 2020 AP Calculus AB exam review. As you know, this year's exam is nothing but free response, so that will be our concentration. Today we're going to deal with the differential equation FRQs. Those particular problems have three parts to them. One is a slope field, the other is a tangent line approximation, and the third is finding the particular solution to the differential equation with a given initial condition. We'll concentrate mainly on the second and third points for today, so we're going to concentrate on the tangent line approximations and finding the particular solutions. I will briefly mention the slope fields towards the end. That's really not that big of a deal, and it's hard for me to replicate the graphs here, but it's a fairly easy thing to do. But the main thing I'm going to concentrate for today is the tangent line approximations and the big guy, the big money getter of these problems, finding the particular solution. So I have several examples I'll do. So for each example, I'll do a tangent line approximation and I'll find a particular solution with a given initial condition. So prior to me getting to it, I just want to remind you of some things for the tangent line approximation. Now on this year's test, you have the great opportunity of being able to utilize your notes. So make sure you have somewhere handy these notes for the tangent line approximation, because if you're given a differential equation problem, a tangent line approximation is a common thing that's asked of you to do. So a couple of things about tangent line approximations. So they're going to give you an initial condition. Generally it'll be written in this type of notation where y of x naught equals y naught. Sometimes it's given as a point, so you know, if it's given as a point, then the point of course is x naught comma y naught. And then you have your differential equation, and you'll evaluate the differential equation at x equals to x naught and y equals to y naught to find your slope. In fact, for the tangent line approximation, finding the slope is really the only real work that you have to do. Everything else is just plugging in items that you already know into the formula. And this is the formula here. So it comes from point slope formula. And for me to approximate the function at a, it's approximated the slope times a minus x naught plus y naught. So basically we're plugging these numbers in. There is no need to distribute the m and put it in slope-intercept form. So basically we're just going to plug the numbers in, and that's going to be our answer. And again, the only number that I'm going to have to find in most cases is going to be the slope. They're going to ask me to approximate it at some value a, so I'm going to know a. They're generally going to give me an initial condition with x naught and y naught, so I'm going to know x naught and y naught. So the only thing I'm going to need to find is m, and m is very simple. I'm just going to evaluate the given differential equation when x is x naught and y is y naught. That's pretty simple. There are some cases where they may give you x naught but not y naught in certain type of problems, but that normally doesn't come up on these type of problems. So I begin by doing a few examples, and for each example I'll find the tangent line approximation of some point, and the point is generally some value that's very close to x naught, and then we'll find a particular solution of several examples. Okay. So example number one, we have the following differential equation. So dy by dx is 1 over 5 times y plus 3 to the 4th power. And the initial condition is y of 0 is negative 2. Alright, so there's the differential equation. First thing we're going to do is we're going to find a tangent line approximation. So for the tangent line approximation, it'll say something like write an equation for the line tangent to the graph of y with the initial condition y of 0 equals negative 2 so it'll be some value, say for, I want to approximate this for x equals 0.3. So we're going to find a tangent line approximation. So we're trying to find the value of f of 0.3. We're trying to approximate the value of f of 0.3 for our tangent line approximation. So again, in that formula, I know A is what they're asking me to approximate at. I know x naught, I know y naught. The only thing I need to find is m. And again, m is evaluating the differential equation at x naught and y naught. So remember, slope is the value of a derivative. A differential equation is a derivative. So sometimes students want to take the derivative of the differential equation, but there's no need to do so. This is implying that the derivative has already been taken. dy by dx is a derivative, hence the term differential equation. So to find the slope m, I'm going to evaluate dy by dx, where x is 0 and y is -2. So if you notice in the differential equation, there isn't an x. It's good news. So I only have to plug in the value of one variable. That's pretty good. So this will be 1 over 5 times -2 plus 3 to the 4th power. So -2 plus 3 is 1. 1 to the 4th power is 1. 1 times 1 over 5 is 1 over 5. So the slope is 1 over 5. What we did right here, finding m, again, is really the only real work we're going to have to do in this problem. Other than that, we just have to remember the formula for the tangent line approximation. So y of, well, let me say f of 0.3 is approximately 1/5 times 0.3, and since x naught is 0, I can just leave it as times 0.3 minus 2. That's the answer. There's no need to distribute this out and get it down to one number. Everything is numerical here. This is a perfect way to just leave your answer just like so. Now, I have to mention on these problems, typically the instructions say write an equation of the tangent line and then use the equation of the tangent line to approximate this given solution. So generally, in most cases, prior to giving this solution, you would write the equation of the tangent line. So the equation of the tangent line would be y is your slope times x minus x naught. Well, in this case, x naught was 0 plus y naught. So generally on these problems, they want you to write the equation of the tangent line first and then use that equation for your approximation. So they generally want this guy and this guy. Okay, so that's the tangent line approximation for this particular example. Now let's look at the big money item, and that's solving the differential equation. So let me remind myself what the differential equation was. 1 over 5 y plus 3 to the 4th. So dy by dx is 1 over 5 y plus 3 to the 4th, and the initial condition, if I remember, was y of 0 is -2. Alright, so generally when they give you these problems, they're giving you a first order separable differential equation. This is a first order separable differential equation. There was one case, one year, where they gave a first order linear differential equation with constant coefficients. But you could have solved that problem without using the integration factor. So, and that's, using the integrating factor is something that's more of a differential equation concept versus a calculus AB concept. So you really don't have to worry about that. You're generally going to see a first order separable differential equation. So if it's a separable differential equation, first thing we have to do is separate. if we don't show our separation, we're guaranteed a score of 0. If we don't show our separation, we're guaranteed a score of 0. So we want to make sure that we show the separation. That's critical. So I'm going to separate. And what does separation mean? Separation means moving y terms with dy and moving dx to the other side with the x terms. And typically when I move the y terms, I'm only going to move y stuff. I'm not going to take coefficients with y. I'm just going to move the y stuff by itself. So in this particular problem, I have this y plus 3 to the 4th. And so I'm going to move it over here. So technically it's going to come down. So I have dy over y plus 3 to the 4th. And then I'm going to move the dx over. And that's going to equal 1 over 5 dx. So sometimes students make mistakes. The y term, sometimes it should be at the bottom and they put it at the top. Sometimes it should be at the top and they put it at the bottom. A very easy rule to remember if your algebra isn't strong is basically if the y term is at the top, it goes to the bottom. And if it's at the bottom, it goes to the top. And if you're saying, well, I don't know if it's at the top or the bottom, then basically it's at the top. Because if it is at the bottom, it's very easy to see. Now, so the first deal is to separate. After you separate, you integrate. So after you separate, you integrate. So now we'll integrate. So if you're looking at this, the right seems pretty simple. The guy on the left maybe is a problem, but the guy on the left is really not that bad. So to look at the guy on the left, I'm going to rewrite it. I'm not integrating, I'm just rewriting this. And I'm going to rewrite this as y plus 3 to the negative 4th power. So I'm going to integrate as y plus 3 to the negative 4th power. Now when I do this integral, technically I'm doing u substitution. I'm going to say u equals y plus 3. But I'm not going to show the u substitution because if u is y plus 3, that means du equals dy. So though it's u substitution, it's very simple u substitution. That can be done without writing all this stuff out. So basically what's going to happen is it's going to be the power rule applied to this. So I'm going to add 1 to negative 4 and get negative 3 and then divide by negative 3. So this particular integral is going to be y plus 3 to the negative 3 over negative 3. And of course the integral of 1 over 5 dx is 1 over 5x plus some constant. So again, I'm pretty sure you're aware, I can put the constant on the right. On the left, I can put the constant on the right. I can put the constant on both sides. Generally, we just like to put the constant, just one constant on the right. Now, next, I like, and most people like to solve for C at this given moment. So at this moment, we like to find a value of C. So we use the initial condition, which generally is given like this. Again, sometimes it may be given as a point, but we're going to use that initial condition to solve for C. There are some people that like manipulate this and put it in y equals and then solve for C. Those are good people, like they're nice people, but most people are going to solve for C now and then try to manipulate and solve for y. So I'm going to solve for C right now. So I'm going to use the initial condition to solve for C. I guess I would say, however, prior to solving for C, if I got something raised to a negative power, I like to move it and put it to a positive power because it's easier to evaluate. So before I solve for C, this y plus 3 to the negative 3rd, I'm just going to move it down here. Okay, so that would make this 1 over negative 3 times y plus 3 to the negative 3rd, and that equals 1 over 5x plus c. Okay, so now I'm just going to utilize the initial condition to solve for c. So I'm going to plug in 0 for x, So this is going to become 0, and since I moved this down, this is no longer a negative 3. That exponent is positive 3. So that's just to the third power. Alright, so I plug in 0. This is gone. Now I'm going to plug in negative 2 for y. If I plug in negative 2 for y, negative 2 plus 3 is 1. 1 cubed is 1. A negative 3 times 1 is 1. So c is negative 1/3. Alright, so we found c is negative 1/3. So that means our differential equation with the value of c plugged in is 1 over negative 3 times y plus 3 cubed, and that equals 1 over 5x minus 1/3. Now everything after this is simple algebra, so we just need to solve for y equals, so we're going to do our little algebraic manipulations and the problem is pretty much over. So we do need to put this in y equals form, so we couldn't just leave it like this and get full points like, hey, I found a value of c, I'm done. No, we do have to put it in y equals form. So probably the first thing you want to do is maybe get rid of this negative 3 down here. So many options. It's kind of like going to a buffet. You don't know what to try. So many different algebraic manipulations you can do right here. But I probably would like to multiply everything by negative 3. So I'm multiplying all the terms by negative 3. Everything, everybody, and their mama is being multiplied by negative 3. So when I multiply this, the negative 3 cancels. I'm left with 1 over y plus 3 cubed. Here would be negative 3 over 5x minus 3 over 5x. And here would be plus 1. Alright, now from that point, what we can do is multiply everything by y plus 3 cubed. You could also, take the cube root of both sides if you want. I'm going to multiply everything by y plus 3 cubed first, and then divide, and then take the cube root. It will come out the same no matter how you did it. So I'm multiplying everything. So all terms are being multiplied by y plus 3 cubed. So when I multiply this guy, it just cancels and I get 1. And on the right side, I have negative 3 over 5x plus 1 times y plus 3 cubed. And of course I couldn't distribute this to this guy because this guy is being raised to a power. That's why you just see it like this. Next thing I would do is divide by this. Again, my objective is to get y by itself. So now I'm going to divide both sides by this guy. And I'll get y plus 3 cubed is 1 over negative 3 over 5x plus 1. And never worry about some of the rules that you did when you were in your elementary algebra classes and maybe your pre-cal classes, where maybe you were told you can't have fractions within fractions or decimals within fractions. We don't care about that here. You can leave a fraction within a fraction. So particularly on a free response, I'm never going to waste a whole bunch of time trying to make things look nice. We like them messy on the free response. So I'm going to leave this just like this. Now I'll take the cube root of both sides. So I'm taking the cube root of both sides. And I'll get y plus 3 is the cube root of 1 over negative 3 over 5x plus 1. And I know that the cube root of 1 is 1, but I'm still going to leave it like that. And the final thing I'll do, of course, is subtract 3 from both sides. So the final answer, the particular solution of the differential equation, would be y equals the cube root of 1 over negative 3 over 5x plus 1 minus 3. So the differential equation was solved successfully. Again, when doing an FRQ, which is what you're going to be doing this year, please don't worry about trying to clean this up. this is beautiful just the way it is. Leave it alone and go on to the next problem. Okay, that was the first example of a differential equation where we did the tangent line approximation and we found a particular solution with a given initial condition. Let me do another example. Alright, so example 2 I have here is dy by dx. Dy by dx is 5 minus y times sine x, and the initial condition is y of pi over 2 is 4. Alright, there's the problem. So again, we'll do the tangent line approximation first. So again, on a tangent line approximation, they're going to ask for a value that's generally close to x naught. So a value close to x naught. Let's say we're going to find the equation of the tangent line and use it to approximate f of, let's say, f of 1.6. So that's a number fairly close to pi over 2. Okay. So again, first I'm going to find the equation of the tangent line, and then I'm going to use it, of course, to approximate f of 1.6. And again, to find the equation of the tangent line, the only real work I have to do is finding the slope. After I find the slope, I'm really just plugging numbers into a formula. And again, I'm going to have that formula very handy for myself this year. So your benefit this year is that you're able to utilize notes. Okay, so let's find m. So m is dy by dx evaluated where x is pi over 2 and y is 4. So let's see what happens. So plug in 4 for y. So 5 minus 4 is 1. So that's 1. 1 times the sine of pi over 2. The sine of pi over 2. Well, the sine of pi over 2 is 1. So the slope is 1. That's a nice slope. So the slope is 1. So the equation of the tangent line then would be y equals the slope. Since it's 1, I don't really have to put anything there. So the slope times x minus x naught. So x minus pi over 2 plus y naught plus 4. There it is. So there's the equation of the tangent line. And now to use it to approximate f of 1.6, f of 1.6 is approximately, now again, this is a tangent line approximation, so we use the approximation symbol. However, if you use the equal sign, you still would get full credit, but technically I'm doing an approximation here. So for the approximation, I'm just going to plug this number in for x, and that's really it. So it will be 1.6 minus pi over 2 plus 4, done. So I hope you can see these tangent line approximations off of these differential equations are very easy to do. Again, one just needs to be able to plug in points into a given differential equation. So of course one needs to know the trig values and basic arithmetic. And one just needs to be familiar with these two equations, and this is what we call easy money in the business. Alright, so that's the equation of the tangent line and the tangent line approximation. Very simple. Now to the big money item, which is finding the particular solution to this differential equation. So it will say something like, find y equals f of x, which is the particular solution to the differential equation with the given initial condition, y of pi over 2 equals 4. Okay, and the same rules apply. So we're going to separate, and then we're going to integrate. and we must show the separation. Even for those brainiacs out there that can separate and integrate this in their head and can find C real quick, we need to show all of this junk. So I'm going to show the separation. So again, I need this y stuff to be with dy, and I need dx to be over here. So this will be dy over 5 minus y, and that will equal sine x dx. So I separate it. So you know the deal. Once we separate, we integrate. So now I integrate. There it is. There it is. So again, this is kind of like a u substitution here. But again, it's very trivial u substitution, because if u is 5 minus y, then that means negative dy is du. So it's almost just the same thing without that minus sign. So I'm going to do u substitution, but again, I'm not going to write the u equal stuff because it's a pretty trivial demonstration of u substitution here. So therefore, the integral of this guy would be negative ln 5 minus y. And technically that guy should be in absolute values because I can't take the log of a negative number. But if you happen to put it in parentheses, you're not going to miss any points. Alright, so that guy is that. The integral of sine is negative cosine. So this is negative cosine x plus some constant. Alright, separate, integrate, use the initial condition to solve for c. So next thing I'm going to do is I'm going to solve for c. So I'm going to plug in pi over 2 for x and 4 for y. So if I plug in pi over 2 for x, cosine of pi over 2 is 0. So negative cosine of pi over 2 is going to be 0. So this will be 0. And if I plug in 4 for y, 5 minus 4 is 1. ln 1 is 0. So c actually is 0. It's a nice value for c. So for this problem, c actually is 0. So we solved for c. It was nice. I enjoyed it. Hope you did as well. And so after we solve for c, after we find the value of c, then we're just trying to put it in y equals form. So what we have right now, when putting in the value of c, is negative ln 5 minus y equals negative cosine x. Alright, so we're going to solve this guy. Now, anytime you have an ln situation, you know what's going to happen is you're going to make these become exponents for e, but you don't want the minus sign there. So anytime you have a minus sign in front of this ln, just multiply everything by negative 1. Or you can think of it as dividing everything by negative 1, but you want this to become positive. So I'm going to multiply everything by negative 1, so that will become positive, and that will become positive. So now I'm going to make these guys coefficients of e. What we call it is we e that junk. So it's a very loose mathematical term, but we like to say it, so we're going to e that junk. And so what that means, I have e to the power of ln 5 minus y equals e to the power of cosine x. And e to the ln anything is going to be anything. So e to the ln 5 minus y is going to equal 5 minus y. So 5 minus y equals e to the cosine x. So that's the reason why we e the junk, is to liberate this y stuff from the ln. That's the main reason we do it. And now it's just basically some basic stuff to get y by itself. So if you would move the 5 to the other side and divide by negative 1. So y would be negative e cosine x plus 5. So again, I moved this 5 to the other side. It became minus 5. I multiplied everything by negative 1, so this became negative, and the minus 5 became plus 5. Differential equation is solved. That was a big money item. We did everything successfully. Next example. So my next example will be dy by dx equals e to the power of x minus y, and my initial condition will be y of 1 equals 0. Y of 1 equals 0. Okay, so again, we're going to do a tangent line approximation. Let's see. So let's do it for f of 1.1. So we'll first find the equation of the tangent line, and then we'll use that to approximate f of 1.1. So again, to find the equation of the tangent line, the only thing I really need to find is the slope. The slope is a differential equation evaluated at x0 and y0. So my slope will be dy by dx evaluated where x is 1 and y is 0. So that would be e to the power of 1 minus 0, which is e to the power of 1, which is e. So my slope is e. So the equation of my tangent line then is y equals e times x minus 1, and then just that, because our y0 is 0, so you can put plus 0, but there's no real need to put plus 0. So that's the equation of the tangent line. And again, to do the approximation, all we have to do is plug in 1.1 for x and we're done. So f of 1.1 is approximately e times 1.1 minus 1. Done. Again, there's no need to subtract these and get 0.1 and multiply by e and put 0.1e. I mean, if you get bored, maybe you want to do that stuff, but really all you have to do is stop right there. So we have the equation of the tangent line, and we've used the equation of the tangent line to approximate the value of f of 1.1. Okay, now let's do the big money item. Let's solve the differential equation with the given initial condition that y of 1 is 0. Now again, this is a separable differential equation. And you may look at it and say, how in the world am I going to separate y from x when they're both up there as exponents? And that's a pretty legitimate concern. But just remember some of the properties of exponents you learned probably in Algebra 1. And you would know, if you think back, that when you subtract exponents, you divide. So that means that dy by dx is equal to e to the x divided by e to the y. So I didn't do any calculus there. That's just rewriting this based off the properties of exponents, which allows me to separate this guy a little easier. So now I can do the separation. Notice the y term is at the bottom, so when I move it over, it's going to be at the top. So this would be e to the y dy equals e to the x dx. So this is very good because the two integrals we have to take. So we have separated, yes. So after you separate, you integrate. But what we're integrating is everybody's favorite integral. In fact, e to the x or e to the whatever is everybody's favorite derivative, because the integral of e to the y dy is e to the y. And the integral of e to the x dx is e to the x plus some constant. So we separated, we integrated, and now we're going to find the value of c utilizing the initial condition. So the initial condition is x is 1 and y is 0. So I'm going to plug in 1 for x and 0 for y. So if I plug in 0 for y here, e to the 0 is 1. And if I plug in 1 for x, e to the 1 is e. So 1 equals e plus c. So that means that c, if you subtract e from both sides, c is 1 minus e. And that's fine for c. So don't think C has to just be some regular number. C can be in terms of E or in terms of pi or in terms of a lot of different things. So this is a very legitimate value for C. We're good. We're in very good shape right here. So now, let's put it in y equals form. So again, our process of finding the particular solutions to these differential equations with the given initial condition is to first separate, then integrate, then use the initial condition to find the value of C, and then after that it's basically an algebra game of putting it in y equals form. So let's see what we have. So this is our guy right here, correct? So e to the y equals e to the x plus 1 minus e. All right. So you should be familiar that e and the natural log are like inverse operations to each other. So before we had in the previous problem, we had ln over here, and so what we did is we e'd the junk, if you recall. Similarly, if we have e over here, we're going to do what we call, where I'm from, we're going to ln the junk. So that means that ln e to the y is going to equal ln e to the x plus 1 minus e. Now, ln e to anything is anything. Because again, understand what a natural log means. A natural log means logarithms are used to find exponents. And a natural log has a base of e. So what this is actually saying, it's saying what power do I have to raise e to in order to get e to the power of y? That power obviously is y. So ln e to the power of anything is going to give you anything. Now, you may be enticed to want to ln each of these individual terms, but that is illegal. So you might be enticed, okay, I'm going to ln e to the x, I'm going to get x. I'm going to do ln 1, and I'm going to get 0. And I'm going to do ln e and get 1. We can't do that. So this guy, when you take the natural log of a sum or difference, you have to just keep them separate like this. So nothing nice happens to this. So this guy stays just the way he is. So nothing can happen to this. So even if you wanted to, there's really nothing that can happen to this. That guy is just going to stay the way he is. Okay, so we'll do one final example. And in this final example, I try to make mention of slope fields. So I have several examples here. So let me choose one that's probably a good one just to kind of use slope fields for an example. And it'll probably be this guy. So the differential equation I'm looking at is dy by dx equals y cubed over x minus 2. So dy by dx equals y cubed over x minus 2. And the given initial condition is y of 3 equals 1. I'll write it as a point. 3 comma 1. And sometimes it's written as a point. So when it's written as a point, it'll say y equals f of x is a particular solution to the differential equation going through the point 3 comma 1. So when you see it written like that, this is just your initial condition. Okay, so let's first find the equation of the tangent line and use it to approximate something that's close to 3. So let's approximate f of 3.4. So again, to do the tangent line and the tangent line approximation, really the only thing we really need to do is find the slope. So let's find the slope. So the slope again is the differential equation evaluated with the values of x and y in the initial condition. So it will be dy by dx where x is 3 and y is 1. So I'm going to plug in 3 for x and 1 for y. Okay, so if I plug in 1 for y, that's 1 cubed, and 3 minus 2 is 1. So again, the slope is 1, another very basic slope. So the equation of the tangent line is y equals, again, the slope is 1, there's no need to write it, x minus x naught, so x minus 3 plus 1. It's there. You can see, very easy. We call it easy money where I'm from. And now to do the approximation, all I'm going to do is turn this guy into that guy. So f of 3.4 is approximately 3.4 minus 3 plus 1. Okay, that's done. So as you get more used to this, you'll go through these a lot faster, and you'll see these are very easy. So now let's do the big money item, shall we? So let's solve this guy. So we're going to solve the differential equation, so we're going to separate it and integrate. So when I do my separation, this y cubed will come down here, so that'll be dy over y cubed equals dx over x minus 2. So one thing to remember, if the x term is at the bottom, it's going to stay at the bottom. So when you move the dx of course is going to the top. Some people would have mistakenly written this as x minus 2 times dx. So this guy stays at the bottom. When I divide by y, divide by y cubed, the y cubed is coming to the bottom, and there's a 1 there, and then I'm multiplying by dx. Okay, so separate, then we integrate, correct? Before the integration, I would like to rewrite y cubed as y to the power of negative 3. So this is y to the power of negative 3 dy equals dx over x minus 2. There's another common misconception. People are familiar with dy over y, that integral is ln y. Sometimes people get a little bit carried away, and they think anytime there's a power of y at the bottom, if you integrate that, you're going to get ln whatever that is. So some people will mistakenly think that the integral of dy over y cubed is ln y cubed. Shame on you. That's absolutely false. So anytime it's dy over a power of the variable other than 1, it's going to be power rule. And if the y is down here at the bottom, or the variable is down here at the bottom, just bring it to the top and change the sign of the exponent, and then just do the power rule. So by the power rule, I'm referring to this guy, where I integrate, say, x to the power of n dx, and I get x to the n plus 1 divided by n plus 1. Easiest rule in book to do, because all you're really doing on such an integral is just adding 1. And you've been adding 1 since you were a snotty-nosed kid, so this should be very simple to do. So to do this integral of y to the power of negative 3, I'm just going to add 1 to negative 3, that's negative 2, and I'm also going to divide by negative 2. So that's y to the power of negative 2 over negative 2. Here, again, I mean, it's trivial. We use substitution, so that's ln x plus x minus 2, ln x minus 2 plus some constant. So we separate it. I wrote the answer without writing the integral symbol. Let me write the integral symbol. Then we integrate it. After I integrate, I like to immediately find the value of c. So except when one of my variables has a negative exponent, I like to move it, either top, bottom, bottom, top, however it has to be moved to make the exponent positive. So I would like to first write this as 1 over negative 2y squared equals ln x minus 2 plus c. Okay, so now I use the initial condition to find the value of c. Now let's see what happens here. I can't wait. The suspense is killing me. So let's see, I'm going to plug in 3 for x. So I plug in 3 for x here. That's ln 3 minus 2. That's ln 1. ln 1 is 0. So that becomes 0. I'm going to plug in 1 for y. And 1 squared is just 1. 1 times negative 2 is just negative 2. So c is going to be negative 1/2. C is negative 1/2. So the issue we have is 1 over negative 2y squared equals ln x plus 2 minus 1/2. So again, so now I'm going to do algebra. I have a lot of things I can do. It's not like certain things I have to do first. Like I can do it in various orders. But what I would like to do first is I would like to multiply everything by -2. And I'm multiplying everything by -2 to get rid of this guy. So everything's being multiplied by -2. And that would give me 1 over y squared equals -2 ln x. I wrote x plus 2 here, but this is clearly x minus 2. Please forgive me. So ln x minus 2 plus 1. And then from there, you can multiply everything, multiply both sides by y squared. I'm going to say this, but I'm not going to show it. Hopefully you follow. So I'm going to multiply everything by y squared. They'll turn to 1 on this side, and it'll be this stuff multiplied by y squared. And then I'm going to divide by that junk. I'm going to divide by this. So what will happen is y squared will equal 1 over -2 ln x minus 2 plus 1. And of course, if this is y squared, then y would be the square root of this junk. And there we have it. So I did want to quickly, before I wrap this up, just make an example of slope fields, which is very elementary, but you should be, I should make a mention of it. So I want to bring back the differential equation that we just solved and talk a little bit about slope fields. So the one we just solved was y cubed over x minus 2. Alright, y cubed over x minus 2. So what will happen for the slope field is they're typically going to give you a graph with 6 or 9 points. The problem would generally be worth 2 points. One for all the 0 slopes, and then the other point for all the slopes which are not 0. So for this particular problem, let's see if I can make a graph and put some points. So I don't want to touch when x is, I don't want to touch when x is 2. Well, I can put that point here and say I put 3 there. And this is 1, 2, say 3. So let's say we have a point here, 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 there, and there. So here's an example. Now I'm not touching, for this particular problem, I'm not touching where x is 2, because when x is 2, that's going to make this undefined. And when it's undefined, you know, you can say, well, it's just going to be a vertical tangent. But there's other things that can happen when the derivative is undefined. So they're not going to touch that on your exam. So when given a problem to find the slope field, there won't be points and a value of x or y that would make the differential equation undefined. So that's why I didn't really touch where x is 2, because again, it'll make the guy undefined. Now when I do these problems, the first thing I want to do is see where my slope is going to be 0. And if I have a rational expression like this, it's going to be 0 where your numerator is 0. Of course, if that value doesn't also make your denominator 0. So obviously when y is 0, my slope is going to be 0 irregardless of the value of x, except of course, you know, when x is 2. But for all other values of x, when y is 0, the slope is going to be 0. So a slope of 0 is a horizontal line And so all you do is draw a horizontal line segment. So this is, so it's just a little line segment like this indicating the slope. So those are all the zero slopes. Then for each of these points, just like you find the slope of the equation of the tangent line, we just plug in the coordinates of these points into the given differential equation. So for instance, this is the point 1, 1. So I'm just going to evaluate the differential equation where x is 1 and y is 1. So let's see what happens. So y is 1, that's y cubed. X is 1, that's 1 minus 2, that's negative 1. So I have 1 divided by negative 1, so the slope is negative 1. So a slope of 1 is 45 degrees, and the negative slope, of course, goes down as you go from left to right. So a slope of negative 1 will look something like that. Then, let's say we look at this point. So this is the point where x is 3 and y is 1. X is 3 and y is 1. So again, I'm plugging in 1 for y and 3 for x. That's 1 over 1. That's a slope of positive 1. So again, a slope of 1 is 45 degrees. Of course, positive is going up as I go from left to right. So it will look something like this. And next, I have the point 1, 3. So I'm plugging in 1 for x and 3 for y. So if I plug in 3 for y, 3 cubed is 27. And 1 minus 2 is negative 1. So that slope is negative 27. So I have a very steep negative slope. So a very steep negative slope. So, I mean, like, when you're doing this, don't like try to fabricate a ruler real quick and get a slope of exactly negative 27. You just know it's going to be a negative slope, which is fairly steep. So just do somewhat of a pretty good approximation. So something like that. Don't lose any sleep over it. So it doesn't. No one's gonna get a ruler and make sure it's exactly negative 27. So just get as close to approximation as you can. And then lastly, I have the point 3, 2. Oh, this is where y. I said this is where y is 3. This is actually where y is 2. So it would be negative 8. And still, that's a pretty good approximation for negative 8. I'm going to leave it. So I said 27, but this is really where y is 2. So the slope right here at the point 1, 2 is negative 8. But that's a pretty good approximation for negative 8. Okay, so the last guy is where x is 3 and y is 2. So 3 minus 2 is 1. 2 cubed is 8. So this slope is positive 8. So pretty much the same looking slope, just as steep, but going in the positive direction. So perhaps something like that. And that's how you do slope fields. So doing slope fields is just like finding the slope of the equation of the tangent line. You just have to make, a little line segment on the lines that represent what that slope is. So that's going to include our review for the differential equations, FRQs. I hope this was of some benefit. And for those that are my students, you're going to see some problems that you're going to have to do that are similar to these type of problems. See you later.